This lesson concerns inverse functions. You want to be sure before you do this lesson that you understand the concept of a function. Recall that a function is a set of ordered pairs where each first coordinate is paired with only one second coordinate. Sometimes we give an alternate definition, such as a function is a rule that assigns to each input element, which we usually consider to be x, a single output element, which normally we call y. Keep in mind that we do not have to use the variables x and y, but those are the traditional customary variables that we use, and so we get used to that idea. We also want to understand the concept of what we mean by an inverse. So the first thing I want to do in this lesson is talk to you a little bit about what does inverse mean. If you have a number x, let's say, if you add 5 to that x value, of course you have a new number there, don't you? If you take that solution and you then subtract 5, what happens? Well, of course we know if we take any number and add 5, if we take that solution and subtract 5, our final result will be the same number x that we started with. So sometimes we say that addition and subtraction undo each other, or that addition and subtraction are inverse operations. Also keep in mind, if we have a quantity x and we multiply times 5, of course we get a new answer, don't we? If we take that solution and divide by 5, what happens? Of course, if we have 5 times x and we divide by 5, again, we are back to x, aren't we? So we say that multiplication and division are also inverse operations. Now, what you've seen here in terms of operations is that inverse operations will undo what the other operation has done. So it brings us back, if you will, to our starting point. When we discuss inverse functions, we're going to see that same concept being carried over to functions. An inverse function is going to undo what the original function did. Let's look back at our paper here, and I'm going to see if I can kind of sketch you a picture of what inverse functions are doing. Let's suppose that we have a set of numbers over here, and I'm going to refer to this as our domain. Recall that the domain contains the numbers that are the inputs, or the independent variable in our function. So we're going to have a number here. Let's just say I take the number 3. Okay, I'm going to have a function that's going to take that 3 and assign it a certain value. Let's write our function down as f of x is equal x plus 5. So in other words, we're going to take this 3, put it in this function, and it's going to give us an answer that I'm going to put over here in this set of numbers over here. Of course, if I put 3 in this function, 3 plus 5 gives me 8, doesn't it? And we remember that this is the range of our function f. Okay? Now, if I'm looking for an inverse function, I'm looking for a function that will take this 8 and bring me back to this 3. So in other words, my function that I'm looking for needs to take 8, okay, so I'm going to call this function g. Let's see what g of x needs to do. If I take 8 and I'm going to do something to it and make it go back to 3, what I could do is subtract 5. So if I put 8 in here, 8 subtract 5, g is going to take me back to that 3, isn't it? And of course we can see if we chose another number over here. Say we took 2. If we put 2 into our function f, 2 plus 5 gives us 7. So we would get a 7 over here. Notice that if we put 7 into this function g, 7 minus 5, g will bring us back to 2. So whenever this happens, we say that functions f and g are inverse functions because one function will undo what the other one has done. Now let me show you this also. Suppose we pick a number over here first. let's say we choose this 8 and we put it into function g. 8 subtract 5, of course, gives me 3. If we then take this 3 and put it into function f, 3 plus 5 brings me back to 8. So when we have inverse functions, it doesn't matter which function we do first. If we do function f followed by function g, we get back to x. If we do g followed by f, we also get back to our original value x. So any x over here, if I do f and then I do g, I'm going to be back to x. Or any x value over here, if I do g and then I do f, I'm going to be back to my x value. So this is the concept of what an inverse function is. Now that we've seen what inverse functions do, let's look at a formal definition for inverse functions. Recall, the idea is two functions that will undo each other, so to speak. Let's look at that definition. Inverse functions. Two functions, f and g, are inverses of one another, provided that f of g of x is equal x for each x in the domain of g, and g of f of x is equal to x for each x in the domain of f. This is equivalent to saying f circle g of x is equal x, and g circle f of x is also equal to x. Now, if you recall composition of functions, this notation right here, f of g of x, notice what's happening. We're picking an x value and putting it into function g first. So x must be in the domain of g. G of x is the result that we get when we put x into function g. We're taking that result and putting it into function f. And notice when we do that, we get x. X is the same thing that we started with. Notice that if we had a 2 here, then there would also be a 2 here. So we would start with 2, put it in g, get an answer, put that answer in f, and get back to 2, and so forth. So this is saying function g followed by function f will give us back to x. And of course this is saying what? If we choose x and put it in function f, take that answer and put it in g, again we get back to x. So this is saying function f followed by function g gives me back x, which is what I started with. Notice here, since f is occurring first, our x has to be in the domain of f. And of course, remember, these circle definitions are just alternate ways of writing this composition f of g of x. Now that we have seen the formal definition, we're going to use this definition to determine if we do have inverse functions. Verify that f of x equals x cubed minus 1 and g of x equals the cube root of x plus 1 are inverse functions. To verify that these are inverse functions, we're going to use the definition. Recall that the first part of the definition said that we had to calculate f of g of x, and what we're supposed to get is x. So let's take a look at that. Notice what we're doing here. G of x happens to be the cube root of x plus 1. So we are putting the cube root of x plus 1 into function f. Well, let's look at function f. Function f has something cubed minus 1. Let's put a parenthesis for that something cubed minus 1, and this is the replacement for that x. Recall, this means this is replacing our variable in function f. So we're going to replace the x right here with the cube root of x plus 1. Now let's simplify this expression. What happens if we cube the cube root? Of course, that simply does what? It removes that radical, doesn't it? So if we cube the cube root, we get the radicand down here, which is x plus 1. And then we're going to bring down our minus 1. And of course, x plus 1 minus 1 gives me x. So this is saying what? If I pick x and put it in G, take that answer and put it in F, so G followed by F gives me back my x. So it brings me back. Now, so far we're okay. That does what we want it to. But we also have to verify that if we do the other composition, G of F of x, that we also get x. So let's look at this. We have G of F of x, notice up here, is x cubed minus 1. So this says we are going to function G, and we're going to replace the variable in G with this quantity here. So let's look at G up here. We're going to use this structure right here. Function G is the cube root of something plus 1. Notice the x. So we're replacing this x with x cubed minus 1. Okay, let's simplify. Of course, when I remove this parenthesis, my negative 1 and plus 1 will add to 0, so I'm only going to have an x cubed left under there. What is the cube root of x cubed? Well, of course, that is x. So again, we're seeing that if we put x into function f, we follow that by going to function g, we get back to x again. So since we have both f of g of x equals x and also g of f of x equals x, then f and g are inverse functions. Okay, so in order to verify that we have inverse functions, we have to do both compositions. Now keep in mind, not all functions are inverses of each other. So if either of these compositions fails to give us x, then we know that our functions are not inverses. Let's take a look at this problem. The question is, are f of x equals 2x plus 1 and g of x equals 1/2 x subtract 1 inverse functions? Well, we're not sure, so we're going to see if we can prove whether they are or not. We're going to do the composition f of g of x. Well, let's replace g of x. G of x is equal 1/2 x minus 1. So here this says we're going to function f right here, and we're going to replace our variable with 1/2 x minus 1. So let's look at function f up here. Function f says we have 2 times our variable plus 1. So this variable is being replaced with 1/2 x minus 1. Now let's simplify. 2 times 1/2 x, of course, gives us 1x, doesn't it? 2 times negative 1 is negative 2. And then we have a plus 1. Notice when we simplify here, we get x minus 1. This does not equal x. So when we started with x and we did g, then when we did f, we did not get back to x, but we got back to 1 less than x. So function f did not undo what function g did. So these are not inverses. When we have inverse functions, we have a special notation that we use. Let's look at this definition for inverse functions. It is customary to use the notation, this is read f inverse. That looks like f to the negative 1 power, but notice how we read it, f inverse. So we use the notation f inverse for the function that is the inverse of f. Now, if we use that notation, instead of using g, so instead of saying f of g of x or g of f of x, we can use this f inverse notation in the place of g. Let me lay this back up here. So actually, this one right here is like this definition, where instead of G, we have used the F inverse notation. And here, instead of G, we have used the F inverse notation. Notice otherwise this is saying the same thing. If I do the composition F followed by F inverse, or F inverse followed by F, I get back to X. And since F occurs first here, I have X in the domain of F. Since F inverse occurs first here, I have the domain of F inverse. And again, this is equivalent to the circle form of these composition functions here. Now, I want you to be sure that you understand this notation and you do not confuse this with an exponent. Note that F inverse of X does not mean, underline that, does not mean 1 over F of X. Recall that in algebra, if you have something like 3 to the negative 1 power, you said that's the same thing as 1 over 3 to the first power, or 1/3. If you had X to the negative 1 power, that was 1 over X, wasn't it? But what we're telling you here is that this symbol, when used with a function name, does not mean the same thing as that symbol when used with either a number or a variable. Here, the negative 1 is an exponent, and we read it negative 1 power. But here, this is simply a symbol that says we have the inverse of function f. Now, let's look at this. A moment ago, we showed that if f of x was x cubed minus 1, and g of x was the cube root of x plus 1, that they were inverse functions. You'll notice here I've just replaced g of x with this notation f inverse of x. We're going to calculate f inverse of 7. So let's look at that. F inverse of 7. This means we're going to the f inverse function, which is right here, and we're replacing x with 7. So I'm going to have the cube root of 7 plus 1, replacing x with 7. Of course, 7 plus 1 gives me 8. The cube root of 8 is 2. So f inverse of 7 is 2. Now, we also want to calculate 1 over f of 7. 1 over f of 7. So we have 1 over f of 7 means we're going to function f right here, and we're replacing x with a 7. So we have 7 cubed subtract 1. Well, obviously, you can see right here that 7 cubed subtract 1 in the denominator with a 1 in the numerator is not going to be equal to this 2 that we got up here. So what we're showing you here is that this does not mean, like the exponent would mean, 1 over. Anytime this symbol is used with a function name, it means inverse function. If you have studied trigonometry, you have seen the trig functions like y equals sine x. Recall that trig functions have inverse trig functions, and we would sometimes write either y equals arc sine of x, or remember this could also be written as inverse sine like this. Notice here again, this symbol is used on the name of a function, and so it does not mean the exponent, negative 1. It means the same thing that the symbol means here with the function name f. Recall at the beginning of the tape I discussed with you that you need to have a good understanding of what a function is, because we're going to find out that not every function has an inverse function. And so I want to review with you what a function is, and then we're going to talk about what we mean by a one-to-one function. In order to have a function, each first coordinate must be paired with only one second coordinate. Sometimes we say each x has only one y. Remember that we had the vertical line test to determine if we had a function or not. The reason that vertical line test works is because when we draw a vertical line on a graph, we have picked an x value. If that vertical line crosses our graph only one time, then that particular x value had only one y value, and thus we satisfied the definition of a function. Now, if a function is 1 to 1, each second coordinate is paired with only one first coordinate, or in other words, each y has only one x. This second condition is not necessary to have a function, but is necessary for our function to be 1 to 1. So 1 to 1 function, the fact that it's a function says each x has one y. 1 to 1 says each y also has one x. We have a theorem. If horizontal lines intersect the graph of a function in at most one point, then f is 1 to 1. Now, I have picked two functions that should be real familiar to you. F of x equals x squared. You know, of course, that this is a parabola with a vertex at the origin 0, 0. Whenever x is either 1 or negative 1, we get a y value of 1. So we go through the point 1, 1 and negative 1, 1. And of course, whenever x is 2 or negative 2, when we square those, we get 4, don't we? So 2, 4, and negative 2, positive 4. And if we sketch in that parabola, our graph would look something like this. Well, notice, of course, this graph passes the vertical line test. It is a function. If we put in an x, we only get one answer for y. But notice that if I do a horizontal line across this graph, my horizontal line crosses the graph more than once. So this said if it intersected the graph in at most one point. Well, this intersects in more than one. This is not 1 to 1. Now, let's see what's happening here. When I draw in this horizontal line, I have picked what? I have picked a y value. And we're seeing for this particular y value, there are two different x values that give me that same y value. In other words, I have the ordered pair, for instance, 2, 4. I also have the ordered pair negative 2, 4 on this graph, don't I? So the same y value has two different x values. This function is not 1 to 1. Now, let's look at the graph of f of x equals x cubed. Again, whenever x is 0, so is y. If x is 1, y is 1. If x is 2, 2 cubed is 8. That's going to be up here. So we get a very steep curve going up like this. Notice if we choose x equals negative 1, if we cube negative 1, y is negative 1, and x equals negative 2 will give me negative 8. So my curve comes down like this. Notice again, this graph would pass the vertical line test. This is a function. Each x has only one y. Notice also that if I cross this graph with horizontal lines anywhere, I will only cross my graph once. So horizontal lines intersect this graph in only one point. Thus, this is 1 to 1. And of course, what we're saying here is that given a particular y value, there's only one x value paired with that y value. So we have this horizontal line test that will determine if we have a 1 to 1 function. Now, let's look at this problem. We are to determine if f of x equals negative 4x plus 12 is 1 to 1. Well, you might perhaps recall what that graph looks like. Let's just do a quick little graph right here. I'm going to put an x-axis right here and a y-axis right here. We'll use this as the origin. We know, of course, this is a linear function. This is like y equals mx plus b here, isn't it? So my y-intercept is 12. Okay, let's count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll cross it 0, 12. My slope is negative 4. So from this point down 1, 2, 3, 4, and to the right 1, I would have this line slanting down like so. Now, as you can see, if I pass horizontal lines across this graph, my horizontal lines will intersect the graph only once. So this is a one-to-one function. Determine if g of x equals the square root of 25 minus x squared is 1-to-1. Well, let's see. Recall that square root here with no sign in front means principal or positive square root. That's important here because whenever we choose an x and we substitute in here, when we get a y value, we're only going to get the positive square root. So each x will only give us one y value answer. This is a function. Now, let's determine if this is 1-to-1. Let's see if we can sketch a graph here of this function. You may recognize what this graph is, but if not, we're going to pick some values here and see what happens. Notice that if I pick an x value of 5, 5 squared is 25. 25 subtract 25 is 0. The square root of 0 is 0. So I have this point right here. Okay. Notice also if I substitute negative 5 in for x, I'm going to square negative 5, which again gives me 25. 25 subtract 25 is 0. So I have this point. Notice also if x is 0, I get the square root of 25. Notice the positive square root or principal square root, which is 5. You can pick some other values of x if you want to. Of course, what happens when we sketch in this graph is we get the semicircle, center at the origin, radius of 5, semicircle. Obviously, when we pass a horizontal line across this graph, it intersects the graph in more than one place. Recall also your tests of symmetry. Notice here, since x is being squared, if we replace x with negative x, we're going to get the same value that we would have for positive x as indicated here, right? Notice if I choose x equals 4 or x equals negative 4, when I square either 4 or negative 4, I get 16. 25 subtract 16 is 9, isn't it? And the square root of 9 would give me 3 in both of those cases. So we can see that there are y values that have two different x values. This function is not 1-to-1. So a 1-to-1 function, it's a function which says each x has only one y. 1-to-1 says each y has only one x. And we've seen how this horizontal line test can help us to determine if we have a 1-to-1 function. I want to look at an alternate definition of 1-to-1 functions because you sometimes see these definitions when you look at textbooks. Let's read these definitions and see that they tell us the same information that we've already seen. A function f is said to be 1-to-1 if for any choice of numbers x1 and x2 in the domain of f, with x1 not equal x2, then f of x1 does not equal f of x2. Well, now that sounds rather complicated, but let's look at what we're saying. This simply means that we are choosing two x values that are different. If we have a 1-to-1 function, different x values will give us different y values. Notice these are the function values or the y values we get when we replace x1 and x2 into the function. Different x values give us different y values. Here's another definition. A function f is 1-to-1 if f of a equals f of b implies a equals b. Let's look at that. F of a means the y value when we substitute a in for x. F of b means the y value when we substitute b in for x. if I have the same y value, this says these x values that I substituted in also have to be the same. In other words, no y in the range is the image of more than one x in the domain. If you study these definitions, you'll see that basically they're saying the same thing we said earlier. Each y has only one x associated with it. Now, we have a theorem that says a function f has an inverse function if and only if f is 1 to 1. So not all functions have inverse functions, only those that are 1 to 1. Let me put this graph back up here on the screen and talk about that for just a second. Recall that the idea of an inverse function is to undo what we had done before. Let's look at this function f of x equals x squared. If I choose the number 2, for instance, and I put it into my function f of x, then my answer is going to be 4, isn't it? Now, my inverse function would need to take 4 and bring me back to 2, wouldn't it? Well, you might be thinking, if I take the square root of 4, I'm going to get 2, and that's true. But then what are you going to do when you need to get negative 2? You see, this 4 might come back to 2, or it might also come back to negative 2. If the 4 comes back to 2 different places, you're saying when you input 4 into this function, you get 2 different answers. That means this is not a function. So the idea here is a function f has an inverse function if and only if f is 1 to 1. So we're saying when we come back, we also want to only get one answer so that we have an inverse function. Now, there's something else that I also want to go back to and talk about just for a second. Recall in the beginning when we did our little picture and we said we picked a number over here in the domain. That was the domain of function f because I picked a value and put it into f, and I got an answer over here of 8, which was in the range of f. Now let's talk about g. Notice that g, we're taking a number here and putting it into g. So this set is the domain of function g. These are the inputs for function g. And I get answers over here, so this set is the range of function g. Now let's look at the implication here. We put these numbers into f, and we get these answers. Domain of f, range of f. We take these numbers and put them in g, so this is the domain of g, and we get these answers, so this is the range of g. So what we're seeing here, when we have inverse functions, the domain of our function f is going to equal the range of our inverse function. I've used g here, but I could also use f inverse. So the domain of our original function is the range of our inverse function. And the range of our original function f is equal to the domain of our inverse function, whether I want to call that function either g or f inverse. So I have written that down as a statement for you. The domain of function f is equal to the range of f inverse, and the range of f inverse is equal to the domain of f inverse. Now, let's see. Let's suppose I have a function f over here. If I input some numbers, let's say I input 2 into f and I get 5. We're not going to particularly put a rule up here, we're just going to kind of do a what if. What if I put a, let's say 7 into f and I get 9? And let's say I put 4 into f and get 3, and so on. What is f inverse going to do? Well, remember, f is going to pick up 2 and pair it up with 5. My inverse needs to take this 5 and do what? Pair it up with 2. So my f inverse function is going to take 5 and bring me back to 2. If f takes 7 to 9, my inverse is going to take 9 to 7, isn't it? If my function takes 4 to 3, my inverse is going to take 3 back to 4. Well, you can see if you look at these ordered pairs, the numbers here, which are my first coordinates, or my domain numbers, end up over here in the range of f inverse. So this is another way of seeing that the domain of function f is the range of f inverse. And notice these numbers, which are the range of function f, end up being here, which is the domain of f inverse. So we want to remember that. Now also, this has something for us to think about when we do some graphing. If function f has the ordered pair 2, 5, then f inverse is going to have the ordered pair 5, 2. In other words, we just interchange the x and y values. You might recall that when you interchange your x and y values, you get symmetry to the line y equals x. So we have that the graphs of f and f inverse are symmetric with respect to the line y equals x. Now, we have already shown earlier in our lesson that f of x equals x cubed minus 1, and f inverse of x is the cube root of x plus 1. Recall, we verified at the beginning of this lesson that these were inverse functions. I'm going to graph these functions here, and we're going to do this just by selecting some ordered pairs, and then we're going to note that symmetry. Let's look at this particular value here. If I choose x to be 0, I have 0 subtract 1 is negative 1. So 0, negative 1 is a point on that graph. If I choose x to be 1, 1 cubed is 1. So 1 subtract 1 is 0. So whenever x is 1, I get 0 for y. If I choose x to be 2, 2 cubed is 8. 8 subtract 1 is 7. So 2, 1, 2, 3, 4, 5, 6, 7. If I choose x to be negative 1, if I cube negative 1, I have negative 1 minus 1 is negative 2. So negative 1 gives me negative 2. And I think you can see if you cube negative 2, negative 8 minus 1 is negative 9. So negative 2 is going to give us negative 9 way down here. So I have this graph right here. Okay, now let's look at this one over here. Now recall, I'm just going to pick some points here. So if x is 0, 0 plus 1 is 1. The cube root of 1 is 1. So whenever x is 0, y is 1, isn't it? Okay, well let me pick some numbers that will make this easy. Let's notice that if I choose x to be 7, 7 plus 1 is 8, isn't it? And I can take the cube root of 8 and get 2. So whenever x is 7, y is going to be 2. So 1, 2, 3, 4, 5, 6, 7, 2. Okay? Notice if I choose x to be negative 1, negative 1 plus 1 is 0. The cube root of 0 is 0. So x equals negative 1 gives me y equals 0. If x is negative 2, negative 2 plus 1 is negative 1. The cube root of negative 1 is negative 1. So whenever x is negative 2, I get negative 1. Well, let's see, what else might I use here? Let's see, if x is negative 9, negative 9 plus 1 is negative 8. The cube root of negative 8 is negative 2, isn't it? So 1, 2, 3, 4, 5, 6, 7, 8, 9 here is going to give me negative 2. What's happening here is this graph is doing this. Now, what I want to show you, recall that y equals x is just our line through 0, 0, 1, 1, 2, 2, and so forth. I'm going to dot that little line in here. And if you notice with that line dotted in there, if you were to fold your paper on that y equals x line, do you see that these two graphs would coincide? Do you see the symmetry that we have with respect to that y equals x line? Now, what that allows us to do, you'll notice we worked kind of hard over here to get this second graph. If I know the graph of this function, all I have to do is to interchange the x and y values to get points on the graph of my inverse function. Notice, for instance, here, if x is 0, y is negative 1. Notice on my inverse function, I have the point negative 1, 0. If x is 1, y is 0. Notice the ordered pair 0, 1 is on my inverse function. So that makes it easy to graph an inverse function if we know the graph of the original function. Graph f of x equals x squared minus 5, and then graph f inverse using symmetry to the line y equals x. Well, first of all, I want to talk about this a little bit because I want you to notice immediately that f of x equals x squared minus 5 is a function, but it is not one-to-one, is it? So in this form, it doesn't have an inverse. So what I'm going to do is restrict my x values. I'm going to let my domain of function f only contain those values of x that are greater than or equal 0. Okay, well let's see. If x is 0, 0 subtract 5 is negative 5. If x is 1, 1 subtract 5 is negative 4. If x is 2, I have 4 subtract 5, which is negative 1. And I'll do one more. If x is 3, I have 9 minus 5 is 4. So you'll see, of course, what I have is half of the parabola x squared minus 5. That function is one-to-one, isn't it? Now, he said to graph f inverse using symmetry to the line y equals x. I'm just going to kind of dot that line in right now so we'll be able to see that symmetry as we take place. Recall, though, this point right here has coordinates 0, negative 5. So if I have 0, negative 5 in function f, I'm going to reverse that and say negative 5, 0 is on f inverse. That would be that point right there. This point had coordinates 1, negative 4. If I reverse that, I have the coordinates negative 4, 1. And of course, this is 2, negative 1, so negative 1, 2. This point was what, 3, 4, so I'm going to go 1, 2, 3, 4, 1, 2, 3. And I will sketch that part. And you can see the symmetry to y equals x. Here, the graph of a one-to-one function is shown. Find the graph of the inverse function, f inverse. Well, we don't even have an equation here, do we? But what we know is that the graph of f inverse is going to be symmetric to this graph of f through the line y equals x. And we've discussed what that means is reversing the ordered pair. So what I'm going to notice here, let's look at this point right here. 1, 2, 3, 4, 2. So that has coordinates negative 4, negative 2, doesn't it? So our inverse is going to have coordinates negative 2, negative 4. Let's graph that. 1, 2, 1, 2, 3, 4. Okay? Now let's go to this point. The coordinates of this point are negative 1, 0. Reversing that, I get 0, negative 1. 0, negative 1. So let's connect those points right there. Okay? Now, this point has coordinates 0, 2. So if I reverse those, I have 2, 0. Right there. Let's connect those. Okay? This point, 1, 2, 3, 4, 1, 2, 3. 4, 3. So reversing, I get 3, 4. 1, 2, 3, 1, 2, 3, 4. Connect those. Now, do you see when I dot in this y equals x that I do have that symmetry to that y equals x line? At this point, I hope you're seeing the relationship in terms of a graph of a function and its inverse. Symmetry to the line y equals x. And of course that indicates we're reversing the x's and the y's. The domain of f is becoming the range of f inverse, and the range of f is becoming the domain of f inverse. Now, keeping that in mind will also give us a clue on how we find inverse functions if we want to know what the equation looks like. To find the inverse function, we're going to interchange the variables x and y. Notice if we interchange the x and y, that's like what we're doing on our graph. It's also like switching domains and ranges, isn't it? So we're going to interchange the variables x and y. Then, if possible, we're going to solve for y in terms of x. And then you'll see once we've done that, if we want to go to the f inverse notation, we'll do that. And then you can check your result. Checking your result would be using that original definition to show that the composition of f inverse of x gives x, or f inverse of f of x gives x. Now the check is an optional part for you. You don't have to do that check unless you're not sure of your solution. Let's take a look at this problem. Find the inverse function for f of x equals 4x plus 6 divided by 5. Now recall that f of x is simply another way of writing y. So I'm going to rewrite this as y equals 4x plus 6 over 5. The first step in finding the inverse is to interchange the x and the y. So I'm going to change this to a y and this to an x. X equals 4y plus 6 divided by 5. Now we'll want to solve for y. So we're going to multiply both sides of this equation by 5. I have 5 times x equals, the 5's over here cancel, 4y plus 6. We'll subtract 6. 5x subtract 6 is equal 4 times y. And then we can divide by 4. So 5x minus 6 divided by 4 is equal to y. Then if we want to, we can rewrite this y as a function notation. Now remember, what we found here is the inverse of this function. So we would write f inverse of x is 5x minus 6 divided by 4. Okay? Now, I'm not going to go through the check with you, but you could certainly do that. So if you'd like to, you can take these two functions and show that if you do the two compositions, in each case, you will get just x as your solution. Find the inverse of f of x equals 2x minus 3 divided by x plus 4. Again, recall what we're going to do is to interchange the x and the y. This, of course, is another symbol for y, so we're going to change this to x. We have x equals, and substituting y over here, we have 2y minus 3 divided by y plus 4. So x equals 2y minus 3 divided by y plus 4. We're going to multiply both sides of this equation by y plus 4. So distributing here, I have xy plus 4x. And of course over here, my y plus 4 cancels, leaving me 2y minus 3. Since I have y on both sides of this equation, I'm going to bring the y's over here and take this term, since it does not contain y, over here. So I will have xy subtract 2y. I'll subtract that 4x over here minus 3. Then what we'll do over here is factor out the y. That leaves me y times x minus 2 equals negative 4x minus 3. And dividing by x minus 2, I have y equals negative 4x minus 3 divided by x minus 2. And again, recall, I can use that f inverse of x notation here instead of y if I prefer. Now, there's a couple things that I want to discuss with you on this example. First of all, let's go back up to this step right here. From here to here, I chose to take those terms containing y to the left-hand side of my equation. We know that in algebra we really don't have to do that. So I want to take this over here and say, what if I had decided to take the y values over here to the right-hand side? So I'm going to leave the 4x over here. I will add the 3. I'll have the 2y over here on the right-hand side, and I'm going to subtract that xy to bring it over there. Now, we're going to factor out y. That leaves me y times 2 minus x. And then we'll divide. So 4x plus 3 divided by 2 minus x is equal to y. And again, I could use that f inverse of x notation. Now, I want you to look at these two solutions. They look a little bit different, but are they really? I want you to notice that in this fraction, if you were to multiply the numerator and denominator both by -1, you would get positive 4x plus 3, which is this numerator. You would get negative x plus 2, which is the same thing as 2 minus x. And of course, it's always legal for us to change a fraction by multiplying its numerator and denominator by the same thing. So what I wanted to point out to you is that sometimes we may get different looking answers that are in fact equivalent solutions. This is really the same function, but just in slightly different form. So either would be a correct way to write the inverse of function f. Now, the other thing that I wanted to point out to you is this. In this form, it's easy for us to determine the domain of function f. The domain of function f is any real number except what? Well, of course, x can't be -4, can it? So this would be all real numbers except 4. Sometimes we write that as the domain of f is x can't be, -4 there, because that would produce a 0 in the denominator. Now, it's a lot of times difficult to look at a function like this and determine the range, isn't it? But I want you to come down here and look at either of these forms, it doesn't really matter, at f inverse. What is the domain of f inverse? Well, let's see, looking at this fraction, it's obvious to us what? X can't be 2, can it? X can't be 2. Remember that the domain of function f is the range of f inverse, and the range of function f is the domain of f inverse. So this set down here, of course I've said x can't be 2, but that's another way of saying what? All reals except 2. So this is the range of function f. Now, when we talk about a range, sometimes if we use the letters, we would say y. Y can't be 2. It's all real numbers except 2. So even though I can't tell that necessarily by simply looking at this equation, because I can determine what the domain of my inverse function is, and I know that the domain of my inverse is the same thing as the range of my original function, then I can determine what that range is. By the same reasoning, I know that the range of my inverse function is the same thing as the domain of my original function. So my range of my inverse is all reals except -4, or if we want to say it, our y values can't be -4 on our inverse function. I have written down a summary of the topics that we have talked about in relationship to these inverse functions. Let's look at our summary. If a function f is 1 to 1, then it has an inverse function, which we use the notation f inverse. So if a function is 1 to 1, then it will have an inverse function. The second thing, the domain of function f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. To verify that f inverse is the inverse of f, you show that the composition f inverse of f of x equals x, and f of f inverse of x also equals x. And last, the graphs of f and f inverse are symmetric with respect to the line y equals x. Recall basically what that means is if we interchange our x and y values, we get points that are on the graph of f inverse. You want to be sure that you have all four of these concepts down in relationship to our inverse functions. This completes our lesson on inverse functions. I hope that what we've done has clarified for you what we mean by an inverse function, how we find an inverse function, how we find the graph of an inverse function, and the other topics that we talked about. I would ask that you would please rewind this tape before you turn it back into the math lab. Thank you very much.